Again, good morning and welcome to Physics 4C here in Norco. As I was saying earlier, basically participation is required in this class. If you don't engage in this class, you're going to miss on at least 10% of the grade. So you really want to engage in this class by attending the class, like you guys are doing right now, or by basically watching the live video later on, and I will let you know on the process and how you ensure that basically you secure your grade also for participation if you do that, okay? So that's how basically this works in this class. Again, if you are in one of my Physics 4B classes, or you were in one of my Physics 4B classes, you know more, at least for those who were, you know how the process works. For those who are currently in my Physics 4B, it's going to be a little similar. Okay, so that's basically the idea of how this works in here. Okay, again, I sent the syllabus for this course to you guys, so hopefully you have had a chance to go through it. One of the things that is very important, and that is you sign up for the Mastering Physics to be able to do your homework. And if you are sitting in Physics 4B, that's going to be useful for you guys because you will need it there too. So the way to log in into Mastering Physics is through Canvas. On Canvas, on the left-hand side, where there is a menu, where there is a home, the modules, and all of the things there on Canvas, there is a button. Usually, it's toward the bottom that says My Lab and Mastering. You click on it and you follow basically the prompts as you're doing that. I think Pearson gives you 2 weeks of access without paying, but after that, they require you to pay. If you have difficulty logging in, please let me know or contact the representative for Pearson. You should not have a problem with that. Okay, so that's basically in a nutshell. By the way, this works for both classes, so I'm going to repeat this later on when we meet with another 4B in the afternoon. So this is one thing. The course basically covers a lot of topics, and it jumps throughout the book that you guys have, namely what is it, University Physics. And we're going to cover a topic that you guys did not cover way back when you were doing Physics 4A, namely fluid dynamics. This is kind of light chapter, and we're going to start with it. It's going to deal with basically hydrostatics and hydrodynamics. Basically, there is only, what, 2 expressions that we're going to explore there. And we're going to finish it hopefully today. Okay, then we're going to delve into, we're going to jump from 12 to chapter 15, where we're going to cover waves. Now we're talking about something very important. It has a lot of applications in engineering. It has a lot of applications in science. It has a lot of applications in physics, of course, and astronomy and everywhere else. Now, the fact that I mentioned that doesn't mean that fluid dynamics is not important. It has its applications also for if you're an engineer, for example, doing fluid dynamics, if you're going to be working in the oil industry, if you're working, for example, with the weather, it has a lot of its own applications too in engineering fields and also science. So that is not to basically downplay the role of the fluid dynamics chapter. Then chapter 16 is just an extension of the discussion we have on waves. Actually, it's going to go into sound waves. Then we're going to discover some interesting phenomena with sound, especially the Doppler effect. And the Doppler effect is not just unique to sound waves. It's actually everywhere. Wherever there is waves, there is a Doppler effect. And it has the main applications are in sound. And there's a lot of technology involved in there. And also in terms of light, such as, for example, in astronomy, it has applications in determining how fast galaxies are moving, and also in terms of police officer giving you tickets for speeding. So they use that too. So it has a lot of applications too. So it's not just in these 2 fields. So it's in science and also technology and even in society. After that, we're going to introduce chapter 17, which is an introduction to the law of the thermodynamics, basically, which is a branch of science independent of everything else. And it's actually a physics topic. It started as an engineering topic. It started as an engineer who was working in the French army asked a simple question. In doing so, he came up with a law. That law later on people didn't like where it sits in the scheme of things. So they pushed it to become the second law of thermodynamics. Then after a while, they discovered, because they needed actually a law before it, and that law before it was the law of conservation of energy. So at that point, they had two laws. One of them is the law of first law, which deals with the energy transfer, and the other one is the second law that Mr. Carnot actually came up with, the French engineer who started the whole thing, at least in terms of formal way for science. The concept of temperature, people dealt with it before that, and they were struggling trying to understand what temperature is and what heat was and things like that. After basically these two laws were entrenched and were solid basically in discussing things like that, they realized that they needed a law before the first law, and the only option available for them, because those are well known by then, was to call it the zeroth law. So we're going to start with the zeroth law, which is the last law to be basically stated, and then we move to the first law, which is the second law to be stated, and then the second law, which is the first law, to be basically talked about. So that's basically how the next 4 chapters after that, chapter 17, 18, 19, and 20. Chapter 18 specifically deals with the molecular, basically, gas theory, and how Mr. Boltzmann basically postulated the existence of tiny particles in the air and was able to explain what temperature was. Okay, so that is basically the 4 chapters. Once we finish chapter 20, we would be right before spring break. Okay, then we have spring break. You guys go home, prepare for the midterm, and you come back ready for the midterm. Because this class is under 16, we only are going to use one of the 2 slots they gave us available for us to use and go and take the exam on campus. Okay, so the midterm is going to be actually in person, not online. So you have to know that the first midterm is going to be in person. There are some rules about going onto campus, and I already stated it on the syllabus. Hopefully, I've had a chance to go through it. First of all, you have to bring a mask with you. I have to download the Guardian app, which probably I forgot to mention but that's actually a campus thing, okay? Guardian app, okay? On your phone, it's a blue app. Make sure you download it from a reliable source. Let me see if I have it in here. Yeah, it has like a shield on it. It's a blue shield on it, okay? And that basically keeps track of your temperature and all of these things to make sure you're not feeling unwell, because we want to protect you by making sure everybody who comes to campus is actually passed through the initial screening through the app, okay? Then you're going, when you come to campus for that day, there will be all kinds of basically security going around there. So they may not allow you to come to class. So make sure that you abide by their rules in terms of wearing a mask, and also in terms of distancing, and in terms also of the number, because we're required not to have more than 16 per classroom who can come and take the exam. So make sure that you abide by the rules. By the time you come into classroom, you will be handed disinfectant wipes, basically, to make sure you clean your area. And not the purple shield, it's the blue. Is it blue or purple? I don't know. Probably with age, the color starts to be different. It looks blue to me, unless it's purple. This is the app. Okay, make sure you enable the location, because if you don't enable the location on it, it's going to say a location is restricted. And the thing with it is, since I'm not going to campus right now, and probably you would do the same thing, you just disable it, because the phone kept on basically bugging me about this issue that this app is using location and it's not in use. So turn it off. So I turned it off. But if I'm going tomorrow to campus, I have to turn it on and go through the questionnaire to make sure that I am in compliance. So And then I have to notify actually the police. Actually, there is a website, there is a form that we have to fill, give the name and the phone number and also the plates of the car and things like that. Which brings me to another important point: when you come into campus and when you park, leave a space between you and the next car. Do not park next to the other car. That's what they're requiring. So when you park between each two cars, there is a space that is empty. So that's how they want it. So the distancing, not just be between people, but also there. And when you sit, you're given a specific seat you're going to sit in it. That is actually the campus trying to keep track of who sits where, to just in case if something happens, they know how to contact you and tell you, hey, you probably need to go and get tested or something like that. So that's for your own safety also. It's not for anything else, okay? There is no need for a parking pass. So you don't need to pay for it. So it's basically waived if you're coming for the exam. The other thing also they want you is no gathering. You come in straight to take your exam. Once you're done, you go straight home. You don't wait and start chatting or exchanging information and things like that. If you need a ride, you can wait for your ride in the designated area around that circle there, but also keep a distance between you and anybody who's in there. Okay, so that's basically how they want this to be handled. I think if the campus does not provide masks, I will have available masks. I'll bring them with me. But chances are you're not going to be allowed to come to class. I mean, if you don't have a mask, so at least wear something before you get into class. If something happens to your mask, I will be more than happy to give you another one, a replacement or whatever, okay? So you're going to clean your seating area, make sure everything is clean. And then when you're also done, before you hand in everything, you make sure also your area is also clean, okay? So just to make sure that the next person who's going to sit in your seat also is going to be at least a little bit at ease, but also you yourself, you're at ease with the situation, that you're not carrying anything. Now, here's a trick. Let's say, for example, you cannot make the exam. It doesn't matter what the reason is. You have to let me know so that we can make up the exam. There is a condition in there on how to make up the exam, okay? You have to turn on the camera, and you have to make sure I can see everything that you're doing in there during the entirety of the exam. That is actually out of fairness to you and to your classmates, because your classmates were under similar condition when they took the exam. You have to also be under those same conditions to take the exam. If for some reason you cannot make up both exams, 1 and 2, because you could say, you know what, I didn't make it because I was not feeling well that day, and the Guardian app did not allow me to go into campus anyway. So just take the 0 for it. I'm going to take a hit for it, and that's fine. Well, if you do that, you're going to get a 0, of course, that's fine. But be mindful of the fact that the final also has the same rules and regulations. Now, if you miss both of them, both exams, you're going to get an incomplete grade, regardless of what your stand in the grade. You might have, for example, a 73, which is a passing grade, but it's not going to work. You're going to have to take at least one of the exams, either proctored online or in person. Okay, so one of the two things must happen. So that is the only way to make sure that you're going to do it. In other words, you cannot have 2 zeros in the 2 exams and be done with it and you expect to pass. So it's not going to work. And I already stated that in the syllabus. So this is in terms of those 2 exams. So after finishing chapter 20, we are in the middle of this spring break. And then we come back again. We start with the first thing is midterm number 1, which is going to be as I described. And then after that, we're going to jump all the way to chapter 33, okay? Which is basically geometrical optics, which is basically what we discovered, the reflection and the refraction of lights and so on and so forth. The next chapter after that is optical devices, basically lenses and mirrors and converging lenses and diverging and all of these things, and how to compound basically devices, how to find the magnification of these devices and so on and so forth, and how to focus an image, for example, when you're taking a camera or something like that. And what does that mean? And mathematically, of course, it means the Taylor series, and you're going to keep the leading term so that all of the rays, when they bounce off of a mirror or when they go through a lens, for example, they have to all meet in the same point to produce a sharp focal, sharp, basically, image, okay? Now, if the approximation doesn't work and you start carrying next terms and the Taylor expansion, you know that in this case, the image is not going to be as sharp. So that's basically by chapter 33 and 34 we would have done with it. Chapter 35 and 36 are really a different approach in a sense. Now Taylor series breaks down miserably in a sense that you're dealing with sizes so small. As a matter of fact, light does not behave as a straight ray. It does not behave in geometry. It's not like a line anymore. As a matter of fact, it behaves like waves, okay? Namely wave optics, okay? And at that point, we'll discover the phenomenon of interference and diffraction, and we go through that thing. They're also trying to get some wonderful devices that are used in spectroscopy and astronomy and everything else, okay? So this is in a nutshell your course. Sounds exciting, doesn't it? Good, okay, at least I have confirmation that at least somebody else is as excited about it as I am. Okay, so this is the topics. We're gonna stop in chapter 36, chapter 37. I hate it the way it is right now in the book because it teaches relativity in one chapter, which is very bad because it messes up that concept horribly. So if I'm gonna do physics 4D, I'm going to probably have a different textbook or enhance chapter 37 to make it more interesting. So let me get into some of the things that we do when we come in onto Canvas. So let me change first of all the view so that you guys have a flavor of how this thing works when you're coming into my class. Of course, you're going to be dealing with the homepage, which is the syllabus, which is mainly what I was talking about in terms of things like that. As I was saying, in the syllabus itself, let me see, is this the syllabus or something else? Excuse me. Oh, man. Okay. Home. Home is actually the same thing. So let me go to the syllabus, okay? So it's everything in here. That's basically, this is the stuff I was talking about, okay? The quizzes and the fact that we have this many quizzes and so on and so forth. The labs, of course, we will have labs in this class. It is what I want to bring your attention to. It's this point in here. Participation is 10%. So how are we going to ensure that you guys are participating and you're not basically drifting until exam time and you decide, you know what, I'm going to see what was the talk about so that they can do these things. So that is one thing that is 10%. Of course, you can skip this and work your grade out of 90, out of 100, and make sure that, I mean, you're shooting for a B, which is not recommended, okay? So that's basically what I'm going to be talking about. These are the topics and stuff like that. So let me talk about how participation works in this class so that you guys have no confusion about it. I'm going to go back to models. Hopefully you guys have had the chance to go through the community rules in terms of how we communicate with one another and be respectful of one another and things like that. Because sometimes we have a tendency, as I see in name, for example, to go on basically reacting and saying things that, like, for example, when we are on Facebook or things like that, that sometimes we don't behave the same way when we are actually dealing with people. When we know the person is in front of us, we usually tend to be more respectful when the person is standing before you than when the person is actually online, which is just a name. So that is basically what this thing is talking about. So please make sure you follow these rules, okay? This is this chapter, basically the key concepts in this chapter that we're going to be covering in here. There is a slight convention that this book uses, and that is the sign thing, okay? The result will be the same. So whether you follow the book or follow the way I'm going to do it, it's the same thing. You're gonna get the same answer, okay? And you will see me a lot doing this thing in here. Later on in chapter 19, when we introduce the work in thermodynamics, I'm going to introduce the same way you guys did it in physics 4A. In this chapter in here, in chapter 19, when they introduce the work, they flip it around and they come up with a negative sign that doesn't make sense to me, and hopefully also doesn't make sense to you. But if you choose to use their book, that's fine, you can use it. but stick with that sign convention. You're going to get the correct answer for the work at the end. Okay, so that's something that you're going to see, and hopefully you will agree with me that it makes more sense to stick with what you guys learned with Physics 4A than having to come up with something that works in chapter 19, but not anywhere else. Okay. Then this thing in here, discussions. This is a typical of what you see on every single unit or every single week when you come into this class, okay? Sometimes the labs, they will not be there because there is only a certain number of labs and there are more weeks than labs. So that's, and sometimes we have exams and things like that. So this might be missing in there, okay? But other than that, this is basic, and also the community rules is only specific to this chapter. So this two, you will see them with, of course, there will be quizzes, there will be other things added back and forth that are added, but this two, they will be essential. They will be there every time you come in, okay? We're going to see the key concepts in here, which is just basically an HTML file with main equations and explanation of what they mean. And then the discussion. So I'm going to click on the discussion right now. And first of all, if I can get into, well, it's not showing me that. Okay, so in this discussion, basically what you see in here is a prompt. You're going to answer the questions that are raised in this video. And this video is actually a recording of the session that we're doing today. So today, for example, we're introducing the course and we're going to go through things like that. And during the course, I will ask 1 up to 5 questions, okay? And those questions, we will discuss them and get the answers to them. You come in here toward the end and you put the answer or answers, okay, to them. Here is how you act. Here is how you do it, okay? You have to have a piece of paper with a pen ready and ready to write whatever you like to write. Take notes, okay, of the key concept that we're covering. But once we hit a point and I tell you this is an item for the discussion for today, it's better to take a note of everything in there, okay? That this is an item that I'm going to be responsible to answer later on. We discuss it, we come up with the answer to it, and you have written everything there is to it. Do not rush immediately and come into here and start posting, because there is a potential for 1 more item during that day, or 2 more items, or 3 more items, or 4 more items up to 5. So you took a note of the first one, and you're doing what you need to do for the second, for the rest of the stuff. And now another item pops up and say, okay, I'll tell you this is the second item that we need to discuss today. And here it is. Here is a question. Finish the calculation, for example, or tell me why this works and this doesn't work. And of course, we will discuss the solution. You have seen the question, you have seen the answer. You come again to the discussion, and item 2 is so and so. If that day only has 2 items, by the time we're done with the class, you have taken notes of the 2 items. If that day has 5 of them, that day you have 5 items, and so on and so forth. Do not rush immediately and come in here and start doing the answers until it's over. Then you come in and answer the prompts. Now, you are not live, you are at home, okay? You couldn't make it, you're sick or whatever, you have something emergency, or your boss told you they have to be here at work during that day. How am I going to do this? Well, that's easy. You come in and watch the recording and do the same thing. Do absolutely the same thing as you're watching it, because you're going to see in item 1 and then item 2. Now they're spread throughout the live session. So some of them will happen in the beginning, and some of them will happen at the end. Some of them will happen in the middle. Maybe all 3 of them will be in the beginning, and you're waiting for the 4th one to show up, and probably it's going to show at the end, or will not show at all, or vice versa. You wait for them until like toward the end. So again, these are not timed, so you cannot cheat your way out of it and say, you know what, I know that they're going to happen somewhere around 30 minutes, so I'm going to skip everything until like 29 minutes and then watch the video, and then I'm done, I'm going to go. So you really have to honestly engage in this class. You have to really know what's going discussed, and then record your answers in a similar fashion, okay? Okay, you say, maybe, hold on, I know there's a shortcut to this, and what is it? Okay, I'm going to go to the discussion, see what everybody else has posted, and then copy it. Why do I have to? I don't have an hour and a half to waste on this thing. The problem with that is you're not going to be able to see what other people have posted unless you post yourself. Okay. Then you can see, oh, then, okay, I have another solution for that problem. I'm going to post anything just to get me to see what other people have been talking about. And then I'm going to copy again and edit my original post. And now I'm in the clear. Well, that's not going to work either because of the following. Canvas keeps tab basically of the initial post and when it was edited. If you edit your initial reply or your initial comment, I'm not going to grade it. Okay. I'm going to just skip that and assume that you did not do your comment, end of the story. So you really have to honestly participate and engage in the class to earn the points for this assignment. This is worth 5 points. Okay. Is this clear on how this participation is working in this class? You guys understand the process? Very good. So, very good. Here is item 1 of the discussion for today. Okay, you're going to come in here. You're going to tell me that this is how the process works for participating in this class. Taking notes of the items that are being discussed and waiting until the lesson is over to come in and put all of the comments in here that are needed. If you cannot make it, I'm going to come in here, watch the video, taking notes, and again post. And after that, I am done. You cannot edit your post once it's posted. So put it in your own words, but that's something that I want to see in there. So that's item 1 for the discussion for the day. Now, because this is the first time, usually I am kind of lenient a little bit. I'm going to tell you upfront that this is the only item for the day today of discussion. Okay. And I will not summarize at the end the items telling you, okay, here is a question, here is the answer, here is a question, here is the answer. Are we in the clear? Okay, beautiful. So we're going to talk about labs and the other things once the time comes for it. But for right now, let's start talking about things that, let me get my OneNote in here first. Okay. The OneNote works on one screen and doesn't work on the other. So I'm going to move this one to the other screen and the OneNote in here and pick up Physics for C. And today is chapter 12. And let me share with you screen 1. Do you guys see my OneNote? Yes or no? Okay, when I am in the screen, I can't see much in here in terms of chat. Let me pull it in here and hopefully good. Okay. So fluid dynamics. Oh man, I should have brought a cup of water with me or coffee or something like that. But imagine with me, this is not hard to do. Okay, the entire chapter should not be difficult to do. Okay, let me get my drawing pen. So what we have in here, we have a fluid. Excuse the drawing. So this is a fluid of something, of some sort. When I say fluid, I sometimes interchangeably use the word water. Okay, so when I'm talking about fluid, think of water all the time. Okay, unless otherwise stated, unless we change it all of a sudden to air or oil or something like that. So that's basically one of the things that we're going to be talking about most of the time. Well, water has a specific, I mean, has a density, which we know the density of water, if you like to index it with the letter W, is 1,000 kilograms per cubic meter. I mean, if I take a cubic meter, which is roughly the size of this separation, I'm trying to get as far as I can so that I can have a rough estimate of what a meter is. Think of it this way and then that way. That is basically what a cubic meter is. You have about 1,000 metric ton of this, okay? And that, if you do the conversion correctly, there is 1,000 grams in a kilogram. There is 100 centimeters in a meter. So if you do the conversion correctly, you find that this is an easy number to remember. It's 1 gram per cubic centimeter. Usually, because people don't like to deal with the thousands, they use the gram per cubic centimeters because the densities all of a sudden are easy to talk about. For example, the density of iron in grams per cubic centimeter is 7.87 or 7.8 grams per cubic centimeter. Okay, so that's iron. The density, for example, of aluminum is 2.7 grams per cubic centimeter. So that's not copper. Copper is denser. This is copper actually. It's aluminum. Okay. So that's some of the things that we have that we know. You guys have experienced these things before, so you know what these things are. I mean, I know that probably some of you have had chemistry before and things like that. So these are the densities, okay? So this is the density of water. Now, the key question that we want to know, another way of describing a fluid is the pressure in it. And the pressure is force per area. Did you guys discuss the concept of pressure in physics for A? Yes, no? Okay, so basically, this is what the pressure, again, it's basically if I exert a force on a specific area, and that's what you see probably some people when they lay, for example, on nails. Nail, if you exert a lot of force on it, that's why it punctures, because it exerts a lot of pressure. But if you have a large surface, for example, like for example, an elephant with very wide legs, then that exerts less pressure because the area is big. So when the area is big, there is less pressure. Okay, so that's how the concept of pressure comes about. In the case of units, first of all, the pressure, the units for the pressure are going to be the units of the force divided by the units of the area, which is meter squared. Oops, meter squared. Okay, so or if you like, the force is in kilogram times an acceleration, which is meter per second squared, divided by meter squared. So the same thing is in kilogram per meter second squared. It's the same thing. Okay, so that's in the system basically that we know, namely kilogram for mass, meter for distance, kilogram for mass, and second for time. And of course, in physics 4A, we introduce another concept, which is the ampere for currents, physics 4B, I'm sorry. And that is the system that is known as the SI system or the Système International, which is really a system to measure the units. So everything can be broken down into these units. Obviously, we have some derived units, like the Newton, for example. The Newton is a combination of kilogram and a meter in a second. As a matter of fact, it's a kilogram meter per second squared. That is what a Newton is. It's not a fundamental unit, but it's also an SI unit, okay? Because it's a combination of the fundamental units, which is in this case, the three of them, meter and kilogram and second. Same thing with this, the units for the pressure. So the pressure has units, a combination of a kilogram and a meter and a second squared, except that it's in this ratio. It's a kilogram over a meter and a second squared. People get tired and sick of calling it kilogram per meter per second squared, so they gave it a name. And that is actually another SI unit called a Pascal, PA. So the unit for the pressure is a Pascal, similar to the Newton, except 1 Pascal is 1 kilogram over 1 meter by 1 second squared. That's exactly the same thing. So this is a Pascal. So it's in honor of Mr. Pascal, who did a lot of work in this area too. Okay, and he was a philosopher and religious person and all kinds of things. Okay, and he has contributions in a lot of things. Theologian, I should say, not a not a religious person. He's got that famous, basically, what is it? Anyway, philosophy, if you guys read about him, he's got something stuff related to God and things like that. Anyway, so that's Pascal. You wonder, because right now we are sitting in a fluid. On top of us, there is the atmosphere. And the atmosphere is a fluid and its pressure. I mean, the pressure in a normal, so this is the atmospheric pressure. In a normal setting, it's 101,300 Pascal. So you and I, as we're sitting right now, we're experiencing this much pressure. Usually it's roughly written 10 to the power 5 Pascal. So the Pascal is a tiny pressure. It's very, very small pressure, okay? You need to remember this number when we do sound, because sound is actually the pressure as it propagates in the atmosphere. And it's going to be a very tiny number as compared to the atmospheric pressure. So the calm air has this much pressure, which is 100,000 pascals, 10 to the power 5 pascals. I mean, 1,300 pascal, we can roughly ignore it in front of 100,000. Okay, it's just a 1% correction to the 100,000. So that's why usually we use this unit. Now there is another unit also, which is the Milli Bar. Okay, that's usually also used in the weather. Okay, so the M bar, and that is 1,000 bars, thousandths of a bar. I'm sorry. Okay, which makes the bar to be 100 bars to be 1 atmospheric pressure. No. Did I have the conversion right or not? So this is to 1,000. I'm sorry, let me get this thing correct. Yes, 100 pascals. I'm sorry, that's not correct. That's stupid. Sorry. That's not correct. That's not the correct conversion. So what I want to write is actually as a bar is 100 pascal. You use this term a lot in weather. Okay, the weatherman talks about the Milli Bar, and it's 997 millibars. So 1,000 millibars actually is 1 ATM, 1 atmospheric pressure. Okay, so that's really the conversions, if you like. But in science, we use a Pascal. We use this one. Okay, we use this unit. And the Pascal, as I was talking about, has this relationship with a kilogram and a meter and second squared. The atmospheric pressure is roughly about 100,000 pascals. In addition, we use the bar also, and 1 bar is 100 pascals. Okay, and you can do the numbers, so find that there 1 atmospheric pressure is 1,000. Did I do this number correct? I think it's the millibar that is 100. Okay, pascals. It's the Milli Bar. Okay, this is not important, but if in case you encounter it in one of the problems, you need to refer the conversion. Most of the times, you will see me using the atmospheric pressure and the Pascal. Okay, so that's basically how we're going to be talking about in this chapter. And here, we are not doing weather. So if somebody is interested in weather, they probably are in the wrong class. Okay, sorry about that. Okay, that's what it takes for you to be excited about fluid dynamics. Anyway, I go back into my situation here, and that is the hydrostatics. I'm going to assume that I have a liquid sitting in a cup, and that liquid is not going anywhere. So this branch of fluid dynamics is called hydrostatics. Okay? So the fluid is not in motion, so the fluid is stationary, it's not going anywhere. The argument in here is, what is the pressure? How does it depend on depth? So that's a question, okay? Let's say, for example, I want to go to the ocean, okay? And the deeper I go in the ocean, of course, the more pressure I'm going to experience. That's basically how we expect it, okay? If I only are just above the surface, then I'm just, at that point, I'm just experiencing what I was talking about earlier, which is the atmospheric pressure. If I go in depth, the further I go, the higher the pressure I expect to find. So I expect the pressure in here to be depth dependent. And that's what I was expecting in here. So the pressure depends on the depth. So I want to know how much pressure there is if I go a certain number of meters. So that's the question that we want to answer, okay? So that's really one of the things. So what I'm going to do is I'm going to take a fluid, a portion of the fluid in a cylinder, an imaginary cylinder in here. Cylinder in the fluid of cross section A. So this cross section is A, and this cross section is A too, okay? I'm going to assume that it's not big enough so that I don't worry about the height of this cylinder, okay? And I want to know how much is the pressure in the same level. Is there a difference between one side and the other? So I'm going to call this side 1, and I'm calling this side 2, and I want to now ask, is the pressure on side 1 different than the pressure on side 2? That is the question I'm interested in. So remember, this is not a real cylinder. This is not a cut from the fluid, because if you cut the fluid, the rest of the fluid will come and fill it. But this is like something that we have to think of to find the difference in pressure in that fluid, okay? So what I'm going to say in here is that this fluid is hydrostatic. It's not in motion at all. So that means the sum of the forces, at least in this side, must be equal. So the force on side 2 on it from this side of the fluid must be compensated by the force on this side to it from this part of the fluid. So that means F1 is equal to F2. Because it's in equilibrium, it's not going anywhere. Because it's hydrostatics. It's not in motion. Because of that, these two forces are equal, and I just define the pressure as the ratio of the force over area. So the force is pressure times area. So on this side, it's a pressure on the side 1 times the area, and it's the same area, by the way, because cylinder is equal to the pressure on the other side times the same area. Cancel the area from both sides, and the two pressures must be equal. So in the case of hydrostatics, the pressure on the same level is the same. So that's one thing. So it doesn't matter where you are in the depth of the fluid, the pressure on that level is the same. So the pressure here everywhere is the same pressure. Of course, it may be different than the pressure in here, but that's another problem. But the pressure on the same level of the fluid must be the same because the fluid is not in motion, because the fluid is not going anywhere, okay? How do I know it's a static or not static? Just put a food colorant in there and see if the colorant starts to move. I know that the water doesn't have any color, but just see it. If it's not moving, that is hydrostatics, okay? So as long as the fluid is not in motion, the pressure on the same level is the same. So I'm going to summarize this thing in here and say that the pressure on the same depth is the same for the fluid in equilibrium. Okay, as long as we are on the same level, the pressure is the same. Let's now explore the idea when we are not on the same level. The difference in pressure, I'm going to take the same fluid as I took before. Okay, here is the fluid. This is the measurement of the depth. So I'm going to call this one H equals to 0. H is not a height, it's a depth. Okay. That is the sign issue that I have with the book. So if I go on an H1, I know the pressure in here is the same pressure everywhere in this depth. If I go on a different height, different depth, that is H2, from this level. So this is H2, by the way, and this is H1, okay? Then the pressure is P2 in here. The question I want to know is, what is the difference in pressure, again, between these two fluids, between these two levels, I'm sorry, of the same fluid? So what I do again, I do the same thing. I'm going to make up an imaginary cylinder of a cross-section A and height H2 minus H1. So that is the height of my made-up cylinder, okay? So that's correct, Justin. So the height is, that's the depth, okay? That's the difference. That's how high the cylinder is, okay? That is really why I'm taking the sign this way, okay? If you take the sign from the bottom, it's going to be minus y2, minus y1, and so on and so forth. So it doesn't matter now. So that's where the discrepancy and the minus sign is coming from, where you take a reference in here. But I'm calling this one depth, how deep I am. So the cylinder has a height of the deepest depth versus the shallowest depth, and that's really how the height is. So what I'm measuring in here is the depth, okay, versus height from the bottom of the tank all the way to where the height level is. Then it becomes the sign is different. I hope you guys are not lost in the sign in your issue. Yes, as long as you know what you're talking about. If you're talking from the surface of the liquid and you're measuring stuff below it, then you're measuring depth in this case, and the height of the cylinder is clearly how deep you went versus how shallow you are, okay? Now, if you are measuring from the bottom of the tank all the way to the surface, then you're measuring from the height of the fluid. And in this case, the height of the cylinder is the highest point from the bottom of the cylinder all the way to the closest point to the cylinder. Yes? Does this make sense to you guys? Okay, very good. The point with this one is that if we do it with depth, we're going to get rid of a minus sign that is not really aesthetic. That's all. If you really care about to keep the way the convention of the book, fine, but the numbers will match. Whatever you answer in here, it's going to match with whatever you're going to do with the other one. Okay. So again, this is just a made up cylinder. It's not real one. Okay, it's just an imaginary cylinder. Okay. So it's not real. You cannot come into the fluid and cut out of it a section, because if you cut out of it a section, the fluid from everywhere, because of the pressure, will come and fill it. So you cannot do that. But this is just a mathematical cylinder, okay? So again, I'm going to ask, this is in equilibrium. That means the force on the top, which I'm going to call F1, exerted by the rest of the fluid, and the force on the bottom, exerted from the bottom, for the rest of the fluid. However, this fluid now has weight, okay? This is how much weight it has. It has mass times G, the mass of the fluid times G. And the mass of the fluid is the density of the fluid times the volume of the fluid times G. And what I mean by the volume, it's this volume. That is the only one that I'm considering. I'm not considering the rest of the fluid. If this force, namely the force of the weight of the fluid, is not balanced, this fluid will fall. Okay. It doesn't matter what the rest of the fluid does. So again, we're going into the condition of equilibrium, and the condition of equilibrium in here dictates that, first of all, on one side, I have this pressure, this force, which is F1. That's pushing down, plus the weight of the fluid, which is the density of the fluid, times the volume, and the volume is the area times the height, okay? Times G, so this is the weight. This is the density, this is the volume, times G. So that is the weight, must be equal to F2, okay? Well, I know, again, by the definition of the force and how it's related to the pressure, the force is the area times pressure, and the area is the same everywhere because it's the same fluid. So it's going to be area A times the pressure P1 from the rest of the fluid in the above, plus rho G times A times H. I just reordered the rho and the G in here, is equal to the area times the pressure P2. From here, cancel the area because it's the same parameter everywhere. Because this whole volume is a made-up volume. This whole cylinder is made up a cylinder. The only physical thing about this cylinder is its height. Because I considered originally a depth of an H2 and a depth of an H1, and I wanted to know what in the world is the difference between them. That is a real thing. So the difference between these two depths is the real. So H is part of the real problem. A is a made-up thing. A is an imaginary cylinder that doesn't exist. So it better not, the answer better not depend on A. Because if it depends on A, we have a disaster before us. We invented something that doesn't exist, and all of a sudden now the difference in pressure depends on that. That is nonsense, okay? So the area cancels. The reason why it doesn't matter, Justin, is because of the fact that it is made up. It's not real. This whole cylinder doesn't exist inside the fluid. I mean, imagine yourself, you have your cup of coffee, and I wish I brought my cup of coffee. I already had it in the morning, okay? And somehow there is a cylinder floating in it. That's nonsense, okay? So what I'm saying in here, inside that cup of coffee, imagine there is a cylinder in there of a cross-section A. So you ask me, how can I make A big? Make it whatever you like. The answer should not depend on it. And that is how mathematically this is translated to make it whatever you like. As tiny or as big as you can make it, the A cancels from both sides. The pressure is real. The density of the coffee is real. G is real. We are on Earth. And the height, now since I'm considering the difference of pressure between a given height, that is real too. So the only thing that, and the pressure in the bottom, that is real. That's the rest of the fluid pushing back on it. So that is, everything now is real. So the expression that we're going to find is the difference in pressure between the bottom minus the difference in pressure between the top. That is, I moved P1 to the other side, by the way, is equal to rho times G times H, okay? So I know the pressure is the same on the same level, that we argued it already. And I know now the difference between the pressures from two levels depends on the height or the depth difference between those two levels, okay? So this is an important result. Okay. When you see me put something in between a rectangle, that is important, okay? That is something that you need to solve problems with it. So that's the argument for it. Now, special case. Special case. I'm going to go into the liquid again and take H1. Remember H here, I wrote it in this fashion. Sometimes you will find it H2 minus H1, okay? The book writes it as Y2 minus Y1, but uses a different convention and pulls a minus sign in here. That's the only difference in there, okay? Because they took the origin different than what I took it, okay? So it's just, if you dare like, just change the system of coordinates to a new system with the origin shifted, and the expression would work the same thing, okay? So I'm going to take H1 to be exactly 0 in my reference frame. H1 is 0. If H1 is 0, I know that this pressure is the atmospheric pressure. And now I go to any depth H below that, okay, below this origin. So in this case, the pressure in this point H, is going to be given by, according to this expression, when I move P1 to the other side, it's going to be atmospheric pressure anyway. The atmospheric pressure plus rho G times H minus 0, which is H. Okay, so that's another way of writing that expression if I change my origin now to make it so that, I mean, if I change H1 so that it really sits on the top of the fluid, just right on the above the fluid where the fluid is sitting. So that is the expression that I find for the pressure. This is called a gauge pressure. So that when you see a word problems and they talk about the gauge pressure, they mean this one. Okay, so this is gauge pressure. What does gauge pressure mean? That is when you have a gate, for example, what it reads. It reads, in addition to the atmospheric pressure, that rho GH. Okay, so if you take, for example, a gauge for the measuring pressure, okay, for your tire, for example, in the car or your bicycle or something, what it's really measuring is not it's measuring in addition to that what it reads. Okay, it's measuring the difference in pressure. So for example, it says 32 psi. That's in addition to the atmospheric pressure. So that is the gauge pressure. So the gauge pressure is in addition to that. So that's really how this thing. I'm sorry, it's the difference between them is the gauge pressure. Okay, P minus P atmospheric. It's this one in this case. Okay. In other words, if, for example, you're driving your car or your bicycle and all of a sudden you have a flat tire, you panic, you call your friend and you tell them, hey, listen, my tire now has no pressure because I'm reading a 0 pressure. You really are not telling the whole story, okay? You're not telling exactly what the other person is, because he will tell you, calm down, man. You still have pressure. You still at least have an atmospheric pressure. You're playing with a basketball and all of a sudden it's flat. It does not, it still has pressure. It has atmospheric pressure. So you technically you should not have to worry about it. Yes? Can you play with a flat ball? So this is what we mean by atmospheric pressure. Okay, it's usually the additional pressure to the atmospheric pressure. But that's how this expression looks like now. Let's say I want to go, how deep can I go underwater before experiencing 1 atmospheric pressure? Okay, that's another interesting question. How deep? I know I'm talking about this one being water. This row can be, if you are dealing, for example, with something else, it can be a row of that medium. By the way, when I was talking about the densities, one of the density that is useful to remember is the density of air. Air, a row of air is equal to 1.29 or 1.2 something, I think 1.29 kilograms per cubic meter, or 1.29 times 10 to the negative 3 grams per cubic centimeter. It's about 1,000 times lighter than water, okay? So that's something that is useful to remember. Air density is a lot less than that of water. It's about 1,000 times less than that of water, okay? So how deep in water can you experience a pressure of another atmospheric pressure in addition to the atmospheric? So you have in here 1 atm, and then you go to a certain depth, H0, and now you experience another atmospheric pressure for a total of 2 atmospheric pressures. So at that point, you come into this expression and you sub for it. So 2 atmospheric pressure is equal to 1 atmospheric pressure plus rho times G times H0. Cancel this one with that one. And now you'll find that H0 satisfies this equation, which is 1 atm divided by rho for water times G, and rho for water. So this is 10 to the power 5, roughly pascals, okay? Divided by rho for the water. Rho for the water is 1,000 kilograms per cubic meter. So we're going to use the meter in here. So it's 10 to the power 3, and G is roughly 10 meters per second. So it's going to be 10 again. So if I simplify and do everything, this is roughly about 10 meters. If you go 10 meters or 32 feet below surface of the water, you're going to be experiencing another atmospheric pressure in addition to the atmospheric pressure. If you go 100 meters, you're going to be experiencing an additional 10 atmospheric pressure to the already existing atmospheric pressure for 11 atmospheric pressure. So actually, you're going to feel a lot of pressure because you're going to be, the water is going to push you from everywhere. You're going to feel basically, if you're going inside the water at 100 meters. At 1,000 meters, which is very deep, which is a kilometer deep, then you're going to be feeling about 100 atmospheric pressure plus 1, 101. That is too much of a pressure that even a person cannot stand it. I mean, you're going to implode for sure. Yet that is exactly how much pressure on the surface of Venus. Venus has about 100 atmospheric pressure on its surface, okay? So that is the reason why we're accustomed to it in here, is because of this thing in here. Which brings me to another point in here. I wish we have another discussion point. This would have been with it. Let's say, for example, we go to the ocean. This is 1,000 meters, which is a kilometer. The deepest oceans are in the Pacific Ocean. near Asia, and that's about 10 times as much, okay? 11 kilometers in depth. So around 1,000 meters or 1 kilometer, in here the pressure is about 100 times, okay? The atmospheric pressure. A person without proper basically equipment cannot really stand that pressure. It's too much of a pressure. You're going to implode for sure. So the question is, how does the fish do it? How does the fish not implode? And we do. Why? It's internal pressure. Do you guys agree with Lawrence? You're almost there. I mean, you have almost the same answer as it should be, which is really because the fish breathes water. So its internal pressure is equal to the external pressure, and therefore it doesn't really implode. So all you have to do then is do like the fish does, and that is breathe the water. You're going to be fine. You're not going to be imploding. Does this sound like a good plan? Yes? Do like the fish does. Breathe the water. Okay. Okay, somebody has the degree. That's basically why the fish survive that much pressure, because they breathe that thing, they adjusted to it. And the reason why we stand this pressure, again, because of this thing in here. I'm showing you behind me the Mars landing tomorrow, that is going to land around noon tomorrow. And the atmospheric pressure is a lot less. It's about 1% the atmospheric pressure in here. So actually we're going to explode if we're in that surface in there without the proper attire too, because our internal pressure is higher than the external pressure. And again, probably we can breathe the atmosphere of Mars, and we should be fine. The only problem with that is 99% carbon dioxide, so we're going to suffocate immediately. So, okay. Anyway, so another interesting question is how high is the column of air? Okay. Column of air, if you do this algebra, is going to be a little bit wrong, because rho air times G times H of air must be equal to an atmospheric pressure on Earth, the one that you're sitting at. But this is rho air is about 10 to the negative 3, basically, kilograms per meter cubed, times G, and G is about 10 meter per second, times the H of air, and this one is equal to 10 to the power 5 Pascal, which is basically units so the H for the air, the height for the air would be 10 to the power 5 divided by 10 to the negative 2. And that is about 10 to the power, what, 7 meters, okay? And 10 to the power 17 meters is about 10 kilometers high, okay? The only problem with this kilometers, the only problem with this analysis is that the density of the air is not constant, is not uniform. So what I plugged in here is not correct when we're dealing with air. Did I say empty? I'm sorry about that, ATM. Okay, thank you for correcting it. Anyway, the point in here is that this analysis is wrong. So if I calculate based on this number, it's about 10 kilometers. 10 kilometers is not correct. The height of the air, basically, if you go above 10 kilometers, you cannot breathe. The air is rarefied there, is true, and that's where planes fly. And that's actually how the Himalayas are high. It's just slightly around these numbers. So the air there is rarefied, and the breathing becomes harder, and the pressure is less. And that's because actually the density that I use in this expression is not correct. The density actually is height dependent, and so is G also, by the way, but it's not going to change G by that much. It's the density that plays a role to allow for the air to extend all the way to hundreds of kilometers actually above the atmosphere. Okay? Albeit at that time, the density is so light that it's ridiculous, okay? So this is basically, in a nutshell, what hydrostatics is. One of the interesting things is the U-tube. Okay, if you take two fluids that don't mix well, for example, and there is a problem, I think problem 62 from the book.
that I urge you guys to work on.
So what we have water, we have oil on one side. The density of oil is given as being 0.8, that of the density of water, okay? And you have water on the other side. And there is like a bridge between them, and that bridge, once it's open, of course, the oil's density is less than that of the water, so the water will actually move to this level, and the fluid, the oil, will move to this height. So this is now the new side of the fluid, the oil, and you're supposed to go and find how high that is, and this is used, actually, the U-tube is used to find the relative density. Okay, all you need is to find this difference in height. And that difference in height, because this point in here is under the same pressure on one side, it's equal to rho of the water times G times H of the water is equal to rho of the fluid, because now it's another fluid, rho oil, times G times the height of the oil, H of the oil. I did not bother to add the atmospheric pressure because it's the same number on both sides, okay? This is the pressure on the same level on this point where they join, and it's the same level in here. It's the same pressure per the first observation that we made for the hydrostatic. Because remember, on the same fluid, because we are still on the same level of the fluid of the water from this side and the same in here, so the atmospheric pressure cancels, and this gives me rho water, and G also cancels afterwards. Is just the ratio of the rho oil, rho water over rho oil, or vice versa, is that of H oil over H of the water. Okay, so this device was used to calculate or to measure the relative pressure. So the U-tube, not the U-tube that you guys are accustomed to nowadays. It's another U-tube where you measure the relative, basically, pressure. Another application is the hydrostatic, basically, application using the Pascal principle that the pressure inside the fluid will propagate in the same fashion. So the hydraulic press. In the hydraulic press, basically what you have in this case is, this is used in mechanical shops a lot to lift heavy objects. You exert a pressure from one side, and this will translate to a same pressure on the other side, okay? Now, let's say, for example, you have a weight in here, W, and you have a force F in here, and you have an area A1, and you have an area A2. The pressure on one side is F over A1. This must be equal to the weight over the area A2. So the force or the weight that you would want to lift in this case is going to be A2 over A1 times the force, okay? So the ratio here of the areas, A2 over A1, can give you exactly how much you can lift, and vice versa, okay? Obviously, the work in here is going to be the force times displacement, and the work in here is going to be this force times this displacement, and the work is going to be the same. So the efficiency of this machine is still at best is going to be 100%, okay? So you're going to find this expression, and probably you can work it out, as long as the pressure, and that's one of the principles that we, the Pascal principle, is going to propagate the same, because at every given simple level, it's the same thing. So as you move it this way, the other one will move the same distance, and the force is the same. The pressure is, the pressure is the same. The force depends on the cross section. So in other words, F over A1 is equal to W over A2, the weight in this case over A2, and you can work the algebra, how much effort, that's usually referred to as an effort, and this is how much load, how much effort would you need to move that load, and how can you adjust the forces so that you do the least effort to achieve lifting the heaviest load. It reposes through this expression, okay? So again, I'm not really going to delve into a lot of these details. I'm going to move on to hydrodynamics. Any questions? It all resides on this idea in here. First of all, this expression that I put in parentheses, and this one, and the fact that the pressure is defined as the ratio of the force over the area. Any questions before we can move on to the next topic in here? I want to get at least an example or two in here to be done on this problem. And the example I have in mind right now is that involving Bernoulli's equation, which is coming into hydrodynamics. So, or what's the other example that I have in mind in here? Hold on. I have two problems that I want to do with you guys in class, and problems are 86 from the 15th edition. Does everybody have the 15th edition? By the way, when you guys do the homework, you should be able to get the e-text version of the 15th edition, okay? So if you guys don't have that, you can always get it online. So that's a required thing in there. Let me check chapter 12 again from the 14th edition to make sure that you guys have the same problems and we're not. Here's the problems. It's problem 86 also. So both of them are problem 86 from the two editions, which really brings me to another point, and that is most of the times there is very little difference between the two editions, okay? The other problem that I'm thinking that we should do also in class, and that is problem 73 from the 15th edition, and that problem 73 from the 15th edition should be problem 73, no, it's not 73. Well, it's problem 71 from the 14th edition. Problem 71 from the 14th edition or 73 from the 15th edition, it's the same problem, okay? And the other problem that I mentioned, problem 58 from the 14th edition is the same problem as problem 62 from the 15th edition. Now, these problems, when we do them in class, you guys have to really, these problems have to really be, once I do these problems, you guys are responsible for making sure that you know how to solve them. We're going to do them in class, okay? Justin, please ask questions, guys. Don't leave it toward the end in there, and then at the end, especially when we do examples and we solve problems, I'm hoping that it's going to be clear enough for you guys to do them, okay? So problem, I'm looking at problem 86. Do you guys have the book? If you have the book, please look at it again. Problem 86 from both books, it has, from both editions, it says you have a bucket containing an unknown liquid. You also have a cube-shaped wooden block that you measure to be 8 centimeters on a side, but you don't know the mass. Oh, we didn't need to get into another law that we did not cover. So we're not really ready to do this stuff in there. So let's get into something that is related to the lab first, and then we're going to do hydrodynamics later, okay? So, and that is the law that we need to talk about is the Mr. I forgot his name. Forgot his name. It's the buoyancy, okay? So basically, if I take an object and immerse it in a liquid, now this is a different object, and immerse it in liquid, it's going to displace an amount of fluid that is this much, okay? Well, the law in here basically states that this liquid will, the liquid will exert a force, which is called F buoyancy, and that's what you're going to be experimenting with it in the lab, is equal to the weight of the displaced liquid, okay? So any liquid that is either completely immersed or partially submerged inside a liquid will be subject to this force, the force of buoyancy, and the force of buoyancy is equal to the weight of the displaced liquid, Okay, so this is an important law. That's what the problem 86 is talking about. So I want you guys and this is what the lab is all about, basically. So you're going to take different materials and you dump them into the liquid, and you will see how much liquid, basically how much the height in this case, because the cross section is probably given to you, A is given, and the height in this case. So the displaced liquid is going to be rho times the volume, which is this in this case A times H, okay? So that's the volume. So this is the mass. Of course, don't forget to multiply this by G. And this is the weight of the displaced liquid, okay? So if you know the area, and if you know H, and if you know G, then you can find that value. Or if you know the volume of this object, if you know the volume of this object, and this object is a non-porous object, meaning the fluid does not go into it, then when it's submerged or it's partially submerged, how much is it submerged in it? Then you know the volume of the displaced liquid is going to be exactly the volume of the object itself. Times, of course, the rho of the water times G, that is the weight of the displaced fluid, okay? And that is the force of buoyancy in this case. This is the force that the object, it's who came out and said that Eureka, I found it. The Greek. No. I lost the name. I think I'm getting old, okay? So this is the force of buoyancy, okay? So this is what you will need to do problem 86. Once we meet, I was hoping to finish the entire chapter. So right now we still have about less than 10 minutes to finish this class. So, and typically this is fine, I mean, because we just basically barely started. So once we meet again, we're going to get into this problem 86. I'm going to give the problems from the 15th edition, 86. And also once we're ready, we're going to do, first of all, Bernoulli's equation, which is very important in this chapter. By far, probably it's the most important thing that we need to cover. And Bernoulli's equation basically tells me the conservation of energy in this case, that the kinetic energy on any side of the fluid, because now I'm dropping the area because I'm calculating pressures, plus the gravitational potential energy, which is in this case, the weight times the height. But in this case, I'm dropping again the area because this is supposed to be multiplied by the area to find the actual volume. This is the actual weight, plus the pressure. And again, I'm dropping the area because the force divided by the pressure is the area. So this entire expression is missing the area in it, is constant. And that is really what this expression is: 1/2 of mass times velocity squared, that is the kinetic energy, plus mgh, that is actually the potential energy in this case, and plus P, which is in this case the pressure, which is equal, again, force over area. If I cancel area everywhere, this term is constant in a fluid, okay? So this is Bernoulli's equation. We're gonna need to derive this expression. Once we derive it, we're gonna do problem 73 in the 15th edition or 71 in the 14th edition. It's the same problem, okay? That's probably the highlight of this book. This chapter is being able to do these problems. The reason why 86 is crucial is because it's all data. It gives you a bunch of data, and you're supposed to analyze the data and answer the problem. I do this a lot, whether in physics 4B or physics 4C or physics 4D, even if I'm doing that. In any calc-based course, there are typical problems that you're supposed to analyze the data and come up with the slopes and interpretation of graphs and answer the questions. And you're going to expect that in an exam environment too. So you're going to expect questions like this one in exams. So you should be able to do that, because that's what we do as physicists. We go and measure things. We try to interpret them based on how the independent variable in this case depends on, the independent variable in this case depends on the dependent variable in this case, okay? That is basically what we do a lot. So you really need to analyze this data and be able to do it. I'm going to use Excel and make sure that you guys are familiar with its functionality and get to some basic functions, including the slope function and other things in there. And problem 73 is a little bit more calc-based, basically, problem. So that is also typical of problems that we would do in class. So hopefully you guys will be familiar with it and get to do these problems. And then the other problem, depending if we have time, whether or not we tackle it or not, it's kind of easy problem. It's exactly this thing that I was talking about in here. It's actually this problem, okay? With an 80% basically density of the oil versus that of the fluid. So, and that is problem 62, and I think it's problem 58 from the 15th edition, 14th edition, 58. And if you happen to use this 15th edition, problem 86 is the same for both editions, okay? So, unless you guys have a question so far about this or the process, this video should be available sometime today. And hopefully you guys at least be able to participate in this class, engage in it. Don't let things that are not clear to basically be passing by. You really need to have them clarified. If I promise that we will do an example with something and that is not clear to you and you would want to hold on to it, wait until then. And you would want to wait until then, do that too. But if I forget to do the example that I'm supposed to do, or I forget to do a promise, please remind me, okay? Make sure that I am held to basically whatever the high standard that you guys can have in terms of what I tell you to do. So if I promise you to do something, say, hey, and we're in something else and we move on and forget, and especially the fact that I'm teaching 5 classes nowadays is kind of busy a little bit, so I may forget. It's not I will forget, okay, let's put it this way. I will forget. So I'm counting on you guys to come in and say, hey, we're supposed to do these problems, and you promise that at least we tackle these 2 problems. I know that you said problem 62, depending on whether or not we get time to doing it or not, but at least you promised problem 86 because you're saying it's a big deal, and problem 73 because you think it's a big deal. So we want to make sure that we have a full understanding at least of these 2 problems and how to tackle problem 62, and also how to understand this Bernoulli's equation thing that you think that it's important for us to take from this chapter, okay? Is this, sounds like it's a good plan? Good, okay. So I'm counting on you guys to make this class more interesting and more engaging, and I hope to see you guys on Monday. We have lecture and lab on that day, and the lab is all about basically the last thing I mentioned, which is the law of buoyancy. This lab, I used it in the last semester, and it worked beautifully, so I'm hoping that you guys will not have difficulty in it. Part of the lab actually is you're going to build your own boat at home using paper, okay? So if you can make a video, short video, no more than 5-minute video for it and demonstrating how it's working, that's great. If not, you're required at least to submit the image of it, the picture of it, okay? That's something that you're gonna be building. Okay. I will see you guys on Monday, and if you can make it tomorrow, I'm gonna try to send a message, because actually when I was doing the lecture, the lady called me. That's why I was a little bit distracted from the STEM Center, because tomorrow we have an event with the STEM Center for the Mars landing. And I'm hoping that maybe if you guys have time, you join us around lunchtime. Okay, see you guys. Let me stop the recording.